Alright, I wanted to start the next section here on your own, just so we can get finished with it, so that you can take your test on Chapter 3 by the end of the week. So this one's derivatives of trig functions, which I know trig functions is like probably our weakest area. So to start, we're just going to do a little review, and we're going to graph the sine of x without a graphing calculator. Or I shouldn't say I am going to do that just to kind of remind you how it works. So there we go. And if you remember anything about this, you know the period is 2 pi, right? It repeats every 2 pi. Down here, and then I'm going to go by like, I'll go like pi, 2 pi, 3 pi. So here's pi over 2, and here's, remember we struggled with fractions, 3 pi over 2, that'd be 4 pi over 2, 5 pi over 2, and here's the pi over 4s, which I'm not going to write in, I'm just going to put little tick marks. Alright, so we got our x-axis down. I'm not going to do the negatives. And we'll go through and just plot some points and then graph the sine. I'll draw myself a little unit circle over there. Hopefully you remember how this works. That's 0 radians, right? This is pi over 2 radians. This is pi. This is 3 pi over 2. This is 2 pi. And we could keep going. That'd be 4 pi over 2. Or no, that's 4 pi over 2. That'd be 5 pi over 2. Round, around, around. So if we're doing sine, remember, the sine is just the y-coordinate of the points around the unit circle. So like at 0, the coordinates of that point, remember, the radius of the circle is 1, so that's 1 comma 0. So the sine of 0 is 0. So over here on our graph, if we plug in 0 for x, the sine of 0 is 0. So we're going to start at 0, 0. We'll just move around like this first. Pi over 2 then. Remember that point is 0, 1. So if I plug in pi over 2 for x, the sine of pi over 2 is 1, right? The sine of pi over 2. Right? It's the y-coordinate of this, so it's 1. So here's negative 1, here's 1. So at pi over 2, we're up at 1. Going over to pi, the sine of pi, well, that point is negative 1, 0, so the sine of pi is 0 again. Down here, that point's 0, negative 1. So the sine of 3 pi over 2 is negative 1. And then it just repeats now. So sine of 2 pi is going to be back to 0. To here, that'd be 5 pi over 2, which is the same as pi over 2. We're going to be back up at 1. Down here. And we can do the intermittent ones too, where like right there, that's like a 45-degree angle. That would be, what, pi over 4. And if you have your unit circle memorized, I believe that's root 2 over 2, comma root 2 over 2. So it's like, if you did pi over 4, it'd be somewhere right in here. Anyway, you could fill in the curve now. And that continues forever. That's what the sine looks like. And these are actually important to know derivatives of, because sine and all the trig functions are useful for things like, it says in your book, heart rhythms, earthquakes, tides, weather. But I would add to that anything that vibrates, any kind of like your suspension on your car, or any machinery, anything that, like I said, anything that vibrates, you can use trig functions to model the vibration, to estimate what's going to happen if it vibrates too much or if you change things. So we'll do one example problem that's kind of like that in a minute, but first we got to figure out what the derivative of sine is. So we'll just think through it here. grab it. So to do the derivative of sine, we're just going to graph it right on the same. And we'll figure out what it is. So we'll just graph it right on the same axes here. So the derivative of sine, remember, derivative just slopes of all these at all these points. So the easiest place to start is where it's 0, right? Slope right there, 0, 0, 0. So if I do the derivative at that point, it's going to be 0. Derivative of there is going to be 0. Derivative of there, 0. So those are the easy ones. The rest, I'm just going to kind of have to tell you. We could do this whole thing where we plug this into the graphing calculator and look at the table and then make the change in the table really small so we can get an approximate slope right there, and then plot all those points on here, and we could sit there and do that, but it takes forever, and I don't know. Or you could just believe me, right there the slope is 1, and right there the slope is 1, which means right there the slope is -1, right there, and then right there the slope is -1. Slope's, and this makes sense, slope's positive through there, and then it hits 0, so, but it gets smaller and smaller. And then after that the slope goes negative, so then this derivative comes down negative, and you end up with this, which looks really close to the original sine graph. Anyone who remembers anything about this, you might recognize this light blue one. Let's see. If I plug in 0 and I get 1, that's a horrible way of describing it. The light blue one, that's the cos of x. It works out like that, right? Cosine of 0 is 1. Cosine, hey, it's 1. If I do the cosine of pi over 2, I get 0, right? Here's the x-coordinate of pi over 2, I get 0. If I do pi, the cosine of pi is -1. It works. So the derivative of sine is cosine. Crazy how that works out. I'll spare you the trouble of listening to me talk. If we do a cosine of x, the derivative of cosine of x is actually negative sine of x. Don't really want to go through that one. So those are just two things you're just going to have to remember. Basically memorization. Derivative of sine is cosine. Derivative of cosine is negative sine. So now just do a couple problems here. So we're just going to find the derivatives of these two. Now I'm just going to do a couple hard ones. The ones in your homework will be a lot easier. Or I'll start with an easy one. Just make it up here, like y equals 3x plus the cosine of x. So all you gotta do there, if you're doing the derivative of that, remember if it's addition, you just do the derivative of each one. So your derivative of 3x is just 3. Your derivative of cosine of x would be negative sine of x. That would be your answer. 3 minus the sine of x. A little harder. Let's see, where's the one I want to do? Y equals x squared times the sine of x. This is not addition. We've got x squared multiplied by the sine of x. So you're going to have to use product rule. Product rule is easy. So derivative dy dx. Remember, it's just uv prime plus vu prime. Or I just do take the first one times the derivative of the second one. Well, the derivative of sine, what was that? Cosine. So derivative of that is cosine plus the second one times the derivative of the first one. Derivative of x squared is 2x. So really, you can't really do much with that. That's your answer. X squared times the cos of x plus 2x times the sine of x would be the way you'd write that. dy over dx. So some of these can get pretty ugly. More. Let's do y equals, oops, cos of x divided by 1 minus the sine of x. So that's quotient rule. Here's uv. Some of you got quotient rule wrong on your quiz. You got it backwards. That's just lack of memorization. My way is low d high minus high d low over low squared. Some of you switched this one and this one, which makes it the whole thing wrong because then you're subtracting the wrong one. Anyway, so doing the derivative of that, I take the bottom, 1 minus the sine of x, times the derivative of the top. Derivative of cosine is negative sine, minus the top, times the derivative of the bottom. Well, derivative of 1 is 0, so the derivative of negative sine. Here's where it gets a little weird. You got negative sine. So when you do the derivative of that, you got to switch it. So the derivative of sine, oh wait, no, sine. I'm thinking cosine. That's okay. So the derivative of sine, negative sine is negative cosine. So you don't have to switch it. Got it backwards. I was thinking if you had negative cosine of x and you did the derivative of that, well, the derivative of cosine is negative sine, right? But you still have that negative in front, so you'd have positive sine of x for the derivative of negative cosine. If you've got a number in front of these, it's kind of like you just leave it out there. It's like if you had 3 times the cosine of x and you wanted to do the derivative of that, it would just be, you would still have negative sine of x, but it would just be negative 3 sine of x. So you just leave that coefficient out there. So back to this one. Doing the derivative of negative sine, you leave that negative out there and just change it to cosine. All divided by the bottom squared. Now we could simplify this, do a little distributive property. I'm running out of room in my paper here. So I get negative sine of x plus, if you have sine times sine, that's sine squared of x. And then negative cosine times negative cosine would be plus cosine squared of x all over 1 minus the sine of x squared. And now this is where we're going to get stuck and we're going to be in trouble because we never learned trig identities. This is the most simple example of a trig identity. You have sine of x, sine squared of x plus cosine squared of x. Well, just a brief explanation of how that works. Remember, on our unit circle, we're just thinking about triangles. Sine is this way, right? The sine of this value is the y-coordinate, so you get sine. You can think of it as this length of a triangle, and the cosine, you can think of it as that length. So if you do sine squared plus cosine squared, it's just Pythagorean theorem. It'll equal the length of this side squared. Well, we know in the unit circle, the length of that side is 1. So 1 squared is just 1. So these are called trig identities. We might have to do a few more of these later this year. But for now, there's one that whenever you see sine squared of x plus cosine squared of x, that's the same thing as just 1. So now we have negative sine of x plus 1 over 1 minus sine of x squared. Your homework, I won't give you any with any identities in it, or I don't think I did. I hope not. If I did, you'll probably just get to a point like that and just have to stop. So getting to this, we see, well, the top and the bottom are the same, right? Negative sine of x plus, that's the same as 1 minus the sine of x. Well, we have 1 minus sine of x over 1 minus sine of x squared, so we can get rid of one of those. And our final answer would be 1 over 1 minus the sine of x. So these can get ugly really fast. Probably one of the hardest parts of this class will be doing these, depending on the ones I pick. Some of them are pretty simple and straightforward, like this. Some of them, this is actually a pretty simple one also, because that's an easy identity, but there are others that are a little more tricky. Here, one more example problem called simple harmonic motion. Harmonic motion is just, like I said, things that vibrate or oscillate. In this case, the example is a weight attached to a spring and at rest. So like if no one's touching it, the weight hangs right there at 0. But in this problem, we're going to take that weight and pull it down to here and then let it go. So the spring is going to pull it up and then it's going to sit there and bounce back and forth on the spring. The reason it says simple harmonic motion is because in this problem, and in all of the problems we're going to do in this class, we don't take into account anything like friction. We just assume that it's going to bounce back and forth from -5 to 5 forever. The only thing that's acting on it is gravity. So the spring will pull it up, and when it hits the top, gravity will pull it back down to -5, and then it'll sit there. Okay, so non-simple, just harmonic motion, that gets crazy, that gets hard. Those are like classes I took, and if you're going to do engineering, you're going to have to learn crazy hard stuff like that, where we do take into account friction. This problem, the way they do it in the book, I don't really like it, because they define the rest position as 0, and down here they put this as +5 when they pull it down. I don't know, my brain doesn't work this way. I think of this -5, but you can define your axes however you want. So I guess for the sake of this problem, we'll use this way as positive and up is negative. So it says weight hanging from a spring, you're going to stretch it 5 units beyond its rest position, and it's going to bob up and down like I just explained. The position, so they give us a position function. This equals 5 cosine t. Oops, I'm showing you the answer. Anyway, so I just asked what are the position, or the velocity and acceleration. So just like before, we're just going to do derivatives to find velocity and acceleration functions. So velocity would be the derivative of this. So the derivative of cosine, like I said, you're going to have to memorize these. Derivative of cosine is negative sine, and the 5 just stays chilling out there. So your velocity will just be -5 sine of t. And then acceleration. Acceleration, just the derivative of this one. Well, you just do right here, the derivative of sine is just cosine. The -5 stays the way it is, you don't change it, so it's just -5. Derivative of sine is cosine of t. So that's it, we just did all our derivatives. Then they give us the good old question, describe its motion. Just for the sake of being brief, one thing that's kind of cool, you see the position and the acceleration are just the same except opposite signs, so negative instead of positive. I'll explain that in a minute, but here they graph the velocity and the position. So when the weight gets pulled, remember positive is down, so when the weight gets pulled all the way down, the velocity is 0. Then as it's released and it moves towards the center, the velocity grows more and more negative, right? Because this way is negative, so the velocity is getting bigger going that way, so it's speeding up. Once it goes past this point and starts moving up, the spring is not really acting on it anymore, so it starts slowing down. Remember, the pink is velocity. So now it's slowing down, and when it hits the top, the velocity, right? Position gets all the way down here, -5. So when it hits the top, the velocity is 0. And then gravity is going to pull it back down, so the position is going to come back here, and then the velocity will get positive because it's falling down now. So you can see those in the graphs. Oh, and I talked about the acceleration and position being opposite. It's because right here, if you pull it all the way down and you let go, well, it's going to accelerate up because the spring is pulling it. So your acceleration is just going to be, and it's going to be really big because the further you pull it down, as soon as you let it go, it's going to have the biggest acceleration. When it hits 0, the acceleration is going to be 0, and then it's going to start slowing down. Hope that sink isn't too loud in the background. Okay, so your homework, I know some of those are pretty confusing. Your homework's going to be pretty straightforward, just doing some derivatives and doing a very basic velocity, speed, and acceleration problem right here. No describing, oh, it does say describe the motion. Okay, have fun with that one. So there's your homework right there. Do those 5 problems and that's it.